Let's get going. Welcome to day 2 of ICALEPCS. It's my privilege today to introduce our keynote speaker, Professor Juan Yin. She's the Professor of Experimental Physics at the University of Science and Technology of China. She is also the chief designer of the payload on the MISIA's quantum science satellite. Professor Juan also published more than 40 papers in international journals and has received numerous awards. The title of her talk today is Large-Scale Quantum Communications Network. Please go ahead, Professor. I'm looking forward to hearing your talk.
Well, thanks. Go ahead. And I will share my screen. Can you see my slides?
Yes, we can. Yes,
okay.
It's being presented now.
Good evening, everyone. It's my great honor to give a talk today. I'm Juan Yin, coming from the University of Science and Technology of China. Here I will mainly introduce some of our recent efforts on large-scale quantum communication network. Well, in this it's a combined photo we took during satellites passing through Nanshan ground station in Xinjiang province. You see the background is a galaxy, and the green this green line displays the satellite's orbit. Well, it's very beautiful. And this is our group. Our group leader is Professor Jianwei Pan. We have 2 main projects on large-scale quantum communication. One is quantum science satellite, and the other is national quantum communication backbone between Beijing and Shanghai. And Professor Pan is the chief scientist of both these 2 projects. Professor Chen Zhipeng is the chief engineer of MISIA's quantum science satellite. And Professor Yao Chen is the chief engineer of Beijing-Shanghai quantum backbone network. We have many professors and doctors in Pan's group. And we also belong to the CAS Center for Excellence in Quantum Information and Quantum Physics. From 2003, we start our quantum communication experiments. And during the past 18 years, we had achieved a series of world records in both fiber and free space links. And we realized the first 13-kilometer quantum entanglement distribution and quantum communication in free space in 2005. And the first decoy state protocol in fiber with the secure distance over 100 kilometers in 2007, and then extended to 200 kilometers in 2010. And we kept the 400 kilometers record in fiber since 2016. And in free space channel, we also realized the 100-kilometer quantum entanglement distribution and quantum teleportation. And also the free space quantum key distribution with huge loss and moving platforms to prove the technologies. So after all these successful ground-based simulating experiments, we get the financial support at the end of 2011. And as we all know, MISIA's was launched in 2016. So it has been successfully launched for more than 5 years. With this satellite, we have implemented a series of satellite ground experimental works, such as quantum key distribution based on decoy state source and entangled photon source, respectively, and satellite-based quantum entanglement distribution and ground-to-satellite quantum teleportation. And with the explore the satellite as a trusted relay, we also show the intercontinental quantum key distribution between Beijing and Vienna. The total distance is about 7,600 kilometers. And we also try to test the gravitationally induced decorrelation of entanglement. So obviously, we think missiles is not the end, but the new beginning. It shows the first step towards the truly global scale quantum communication network. On the other hand, we have also constructed the longest quantum key distribution fiber network. It is from Beijing to Shanghai, and with the total length more than 2,000 kilometers. It connects the biggest 4 cities in China: Beijing, Shanghai, Hefei, and Jinan. It covers 1/4 population and 1/3 GDP of China. Until now, we have a lot of users in our fiber network, including banks for data disaster protecting, and the internet companies for data security. And the Beijing terminal is further connected to our Xinlong ground station. The combination of Beijing, Shanghai fiber quantum network and the missile satellite let us have a chance to show the feasibility of the global quantum network. Besides the mentioned quantum experiments in China, MISIS has also already did many quantum downlinks to our colleagues overseas. So I just mentioned we did the Beijing and Vienna intercontinental quantum key distribution. That was in 2017. After that, in 2018, we also did the quantum key distribution to Tenerife. We demonstrated the high-speed European-China quantum key distribution. And in 2019, the MISIS also did the link test to Moscow in Russia, and in 2020 to Matera in Italy. And recently this year, we have get the key generation to Calgary in Canada. And also South Africa and Australia is preparing. So we are so lucky that MISIS is very successful, and it has flying orbit for more than 5 years. But you know, it still has limitations. As a low Earth orbit satellite, it moves fast, which makes the experiment duration is only 6 to 8 minutes for each pass. And the coverage range is about 500 kilometers. And it has to work in the night. Therefore, in order to realize the truly global scale quantum communication, there are still many difficulties and technical challenges to be pushed in the future. We need to make efforts in many aspects, such as quantum constellation with low Earth orbit nanosatellite, the high orbit quantum satellite, and also have to upgrade the present fiber network. And we can see that there are many low Earth orbit quantum satellite plans in the world, in which Singapore has already sent Spooky 1 to space in 2019 and tested in-orbit entangled photon source. And while United States has sent CAPSAT with single photon detectors early this year. And Canada's KeySat will complete maybe in 2022. In the United Kingdom's QUAC will launch and establish the satellite ground link in 2023. Since June 2019, European Union member states have one by one signed to a declaration agreeing to build a secure quantum communication infrastructure across Europe. The European Space Agency is also involved in the project. It will consist of fiber communication networks and satellites, linking national quantum communication networks all over the European Union and worldwide. The aim is for it to be fully functional by 2027, in 6 years. And in June this year, during the G7 Leaders Conference, called Federated Quantum System also announced. So there are many projects, quantum communication network projects all over the world. So here in China, the first thing we have to do is to develop the quantum constellation with low Earth orbit nanosatellite and the lower cost compact quantum key distribution payloads. I want to share with you that now we are developing a nanosatellite with the weight of less than 100 kilograms. And the repetition frequency on the decoy stage is over 600 megahertz, and the real-time key extraction based on laser communication has also been achieved. So if everything goes well, it will be launched early next year, carrying the rocket of the Institute of Mechanics called Zhongke #1. And the compact quantum key distribution payload has been reduced to less than 35 kilograms, which makes it possible to be easily carried by some typical satellite. For example, the classical communication satellite or laser communication satellites. And meanwhile, we are promoting to launch 3 to 5 nanosatellites in 5 years to serve more than 100 users. The large and heavy telescopes we used before in the experiment are not user-friendly, so we also need to significantly reduce the development and costs of the ground station for quantum constellation. So we redesigned the telescope, and you see the weight has been reduced from 13 tons to less than 100 kilograms, and the size has also been reduced a lot. So in a word, the ground stations are now easy to place, install, and use. And with these compact ground stations, we had totally complete many times satellite to ground quantum key distribution at different cities such as Shanghai, Lijiang, Weihai, Mohe, and so. And the safety key rate is about 2 kilobits per second. Well, here is a short video of rapid deployment in Jinan at the end of 2019 and performing satellite-based quantum key distribution in the middle night at the same day. I also want to mention that this year, the quantum key distribution experiment to Calgary also used this compact ground station from China. The second thing we had to do is to overcome problems of short time duration and small coverage range. So we were planning to launch a high orbit quantum satellite using the MEO or GEO satellite. The communication time during one transit will be increased from, I mentioned 6 to 8 minutes to hours. And furthermore, if we can break through Earth's shadow limit, and we will be able to provide 24-hour service of key generation for some specific area. Here is an initial design of the GEO quantum satellite. For the satellite platform, it needs to be ultra-static and stable. And meanwhile, it should have orbital transfer ability. Well, the orbit is higher, so the channel loss will be increased. So in order to overcome the higher channel loss caused by the orbital height, payloads also need to be upgraded. For the photon transmission payloads, large diameter telescope, maybe over 600 millimeter, will be developed. And the divergence angle will be less than 3 microradian, and the tracking accuracy will be accordingly reduced to less than 100 nanoradian. And for the quantum communication payloads, due to the huge channel loss, we should develop ultra-high brightness source, such as gigahertz entanglement for entangled photon source and the decoy state QKD source, and also the high-speed laser communication system. And two types of quantum source have already been developed. You see the decoy state source dedicated for quantum key distribution achieved the repetition rate of 1.25 gigahertz, and the brightness of entangled photon source is almost 2 orders of magnitude higher than that of Messias. And also for the GEO satellite, the big optical telescopes on the ground also should be upgraded. And I mentioned we want to break through the limitation of quantum communication only at night. The difference between daylight and the night, the noise is increased almost 5 magnitude orders. So we have to reduce the background noise greatly to get enough signal to noise ratio. And we all know we can to reduce the noise. We can use the filter technologies from many aspects, such as spectrum, time, and space. For the space filtering, for example, we can choose single mode fibers to receive the photons instead of the multi-mode fibers we used in the Messias experiments to reduce the field of view of the receivers. But you know, due to the atmospheric turbulence, the coupling efficiency of single mode fiber will be very low. And to overcome this problem, we should develop the adaptive optics to achieve enough coupling efficiency. That's the technologies we have to overcome to break through. Well, besides, on the other hand, the present fiber-based network in China also need to be upgraded. The goal of the upgraded backbone network would be safer, faster, and wider coverage. So new protocols such as measurement device independent quantum key distribution, twin field quantum key distribution can be developed to offer a better security and greater transmission distance. For example, in this year, we had demonstrated the 511 kilometer twin field quantum key distribution between two metropolitan areas. And our colleagues also achieved the entanglement of two quantum memories over 22 kilometers, which enable repeater-based quantum communication, paving the way towards building large-scale quantum networks over long distance. Where several new quantum backbones are planning and to build a national quantum backbone fiber network to connect most provinces in China. Where here, this blue line is from Beijing to Shanghai. It's complete, I already mentioned many times. And this green one is from Hefei to Wuhan. It's also complete. And the red one, and the red and the purple line is from Beijing to Wuhan, Wuhan to Guangzhou are under construction. So in the future, we will have a global scale quantum network, which can provide fast response secure communication services for government, overseas agencies, militaries, and so on. Where backbone network on the ground provide secure communication services for distant cities, while metro area networks for inner city nodes. And meanwhile, a quantum constellation with massive low Earth orbit satellite connects the key nodes on the backbone networks and the movable nodes, such as the warships in the ocean. And furthermore, MEO to GEO quantum satellite can continuously provide secure communication service between arbitrary nodes, which can extend the feasibility of the network. So if we can make the global quantum communication network much cheaper, much safer, and more convenient to use, we can make it to be the best choice for future information security. Well, at last, I want to introduce some future prospects. And one of the future applications for the global scale quantum communication network is precise timing information sharing. With optical network and optical frequency transfer, we can obtain almost 4 magnitudes better than microwave scale on long time instability. Such high precision time synchronization also meets the requirement of quantum internet. And interestingly, if combining photons from distributed telescopes worldwide by quantum teleportation in space, we can obtain an effective aperture equivalent to the size of the Earth, and thus an enormous spatial resolution, which enabling us to read on the Earth read on the Earth's license plates floating in Jupiter's orbit in principle. And furthermore, with the global quantum communication network, one can also investigate the fundamental physics at the interface of quantum physics and gravity. So utilizing the future high orbit satellite it's possible to develop an optical clock to promote the long-term stability to the -21 level, or even better, that would achieve an ultra-high precision optical frequency standard and establish a global new time frequency. Furthermore, space-based ultra-high precision optical clocks holds promise for detecting gravitational waves and dark matters. And exploiting these quantum technologies with the help of Chinese moon landing project in the future, we hope to perform entanglement distribution between the Earth and the moon. As the distance between the two detectors will be greater than 1 light second, and both freedom of choice and collapse locality loophole could be closed, we may complete the large-scale test of Bayes inequality with human observers. So that's all. Thank you. Thanks for your attention.
Thank you. That was very interesting. I think we have a few minutes for questions. If anybody wants to ask a question, please raise your hand. Anton, please go ahead. Anton, you can ask your question.
Oh, hi, this is Anton from South Africa. Thank you for the interesting talk. I was wondering how cloud cover affects this. If the ground station is cloud cover, what do you do?
Well, would you please say it again?
Okay. If there are a lot of clouds at the ground station, a laser can't get through the clouds. How do you deal with that on a global scale?
Okay, quantum experiments is first. It's now we use photons, so it's just like laser communication experiments. The clouds would be problems. We cannot the quantum signals cannot transmit through the clouds. So the quantum communication network will be consist of the satellite and the fiber network. So some solution would be that when some place you want to use the key and it's cloudy, then you can connect to some sunny place with the fiber. Another way we think that would be if the ground station is compact and movable and easy to be placed, so it can somehow put it on a plane, so the plane can fly over the cloud. Then it can connect, do experiment with the satellite. But I prefer the fiber solution. Yes.
Thank you very much.
I think we are right on time, so I think we'll conclude the session and we're going to move into the following session. So please have a look on the UVA site, which sessions you would like to attend. And thank you again, Professor, for a really interesting talk. And then I imagine it's over to Scott and Lucas.